Hi, we'll continue the tutorial, parts 3 and 4. Now, part 3, a framework for runtime checking of safety and liveness, including formal specification and automatic state collection and checking. We'll use the same running example we have seen before. So just recall the polling program in this algo. This is the poller process. It sends a question with logic time as the ID to all the responders, the pollee, and wait for each responder. From each responder, we have received some reply with the same logic time as ID. And then it sends the outcome to all the responders. And each of the responder wait to receive the outcome. While waiting, when they receive the question, it sends a reply. Okay, let's see what properties we can specify and how do we check. First, safety. These are two example safety properties. First, the poller has received a reply to the question from each pollee when sending the outcome. If you think about it, this property actually uses information about only one process, because if you are the poller process, you can already check this property, okay? And this is actually easy to see in our program because our program already checks the poller has received the reply from each pollee before it sends the outcome. We use this as an example for several purposes. First, we're contrasting checking this property by a checker, okay? Specify and checking this property by the checker versus the poller itself. This is important if one cannot access internal process. And even if you can access internal process, you didn't write in this high-level algo program, and you might need this because internal can be complex. You're not sure if this property was true. Okay, and the second property is each pollee has received the same outcome when the program ends. This clearly requires checking multiple distributed processes, right? Each of the pollees are separate processes. And this can be checked at the checker, and we can do this conservatively. Okay, so these are the two examples. So to write them precisely, okay, we only have these two little notations that's new. Okay, we've seen sent and received as the sequences of sent and received messages. For each process, you have these two sequences. But now we are talking about multiple processes. So we have this notation p.sent and p.received. Okay, so this is the sent and received of process P, because when you talk about multiple processes together. Okay, and also we use this ideal notation. Okay, just for a couple of slides for formally specifying the property. We write p.sent, okay, p send m to processes queues at the time t, instead of using p send as this function called syntax in Python to queues and clock as t. And similarly for received, p received m from q at t. Okay, and the clause for to, from, and at, each of them is optional. All right, so these are the two processes from the previous slides. I just copied them here. Let's look at the first one. First, look at the part without this underscore part, okay? The poller has received the reply to the question from each pollee. So here there's this the question, right? That's assumed. In order to check something, you have to first know what the question is. So this is the existential quantification, some p sent question with the ID t. That is the question, okay? So for this question, we say each R in responders, okay, that's pollee, has some received reply with the same ID, okay? And remember, p.received is received by p, okay? So for this p sent the question, and each responder, I received a reply from that from the responder, okay? And this is in P's received sequence, okay? Remember this equal means it's matching this equal, and this P, and this equals R, matching this R, okay? So you can see this logic is the same. Each R responder, P has received the reply, okay, for the same ID from R. Now the second half, when sending the outcome, okay, when sending the outcome. So how do I say that outcome? So the same principle, some P sent question, and here's the same, some P sent outcome, okay? And we want to say the polar has received this when sending the outcome. That means they received it before sending the outcome. So we have a new time at the T1, and this clause is extended to say, okay, when receiving reply at the time T2, this T2 has to be before the outcome was sent. So T1 greater than T2. Okay, so this is the whole complete property. All right. The second property, each poly has received the same outcome when the program ends. So the same idea, the same outcome. So I have to say the outcome. So this is the same, P send outcome. I want to say the same, so I have to find that outcome. So I put O in here to bind O, the outcome. And then each R in responder has received outcome that equals that O. Okay, when program ends, so you check this at the end. And liveness, we'll consider these two examples. The polar eventually receives a reply to the question. So this one assumes the question was sent and covers the duration from then to receiving the first reply, okay? Receives a reply. This is the first indication that the polling really started, okay? We use this example to contrast the previous safety property that receives all replies. The second liveness property, eventually each poly receives the outcome. So this assumes an outcome was sent and covers the entire duration of polling. Okay, so this expresses the completion of the entire algorithm. All right, precisely, we again introduce one tiny notation, eventually condition. Okay, so this means eventually condition holds. That is, holds at some point in the duration that starts from the time under discussion. Okay, from the time under discussion to future time. At some point, this thing holds. So these two properties are copied again from previous slides. The poly eventually receives a reply to the question. So you can see that eventually some property holds. In fact, this is the same as S1 property, okay, the first version, the first part without talking about the outcome. The only difference there saying it receives reply from all responder. And here we want to say receive from some responder. Okay, so just change that each to some here. L2, eventually each poly receives the outcome. So this is just eventually, and in fact, this is exactly the same as S2. All right, now for liveness, there's something more interesting. In practice, conceptually, eventually something holds. It's about infinite executions, eventually. At any time it doesn't happen, it might happen later, okay? So in practice, you cannot check something that's infinite. So they are checked against finite executions. So what you do is you impose a bound on when the property should hold, and you report a violation if the property doesn't hold by then. Formally, this actually changes the liveness property to a safety property. So for L1, the first reply is received within a time bound. That's really what it says if you want to make that into a bounded execution, finite execution, okay? So to do this in practice, you estimate or give a time bounds for message passing and the poll filling time. And you can use that to calculate an upper bound on the time from sending the question to receiving the first reply. And then you can be alerted by a timeout if this bound is now met. Okay, so the time bound reached and the first reply has now been received. For L2, programming terminates and S2 holds at the end. Remember, eventually S2. So that's really the implication. So this boils down to checking that the program terminates. So you can impose a time bound for the total program execution time. So that's about specification. We use those ideal notation. Now let's talk about the checking safety and liveness. For checking safety, we consider extending original processes, the P and R, okay, to be checked. Any original process you want to check. So what you do is for each of those processes, when they send or receive a message, they need to send information about the sending and receiving to the checker that's intercepting the messages, okay? And then the checker used that information to check the properties of the original processes, okay? The information about the sending and receiving may include these 4 kinds. First, whether it is a sending or receiving, tagged, sent, or received, respectively. Second, the original message, complete original content. And third, the receiver or receivers for sending, or the sender for receiving. And finally, logical timestamps of the sending or receiving. In practice, you may omit some parts that you don't need, or you can add others just as additional information that helps for checking. But these 4 are enough to sufficient to recover all information. So with the ideal channels for sending information, which means you don't lose messages, then checker can extract the property. So P send message M to process Q at T is the same as checker received sent M to QS at T from P. Okay, send M to QS at T, send M to QS at T. And if P does the sending, the checker would receive that from P. And same for receiving, okay? Checker would received M from Q at T from P, okay? So when we write programs, we just have to write code to send information about sent and received and change from the properties we have before to what checker sees, okay? Here is half the program, but this is all the philosophy. You extend the original processes to send those information. So this requires no change to the original program, okay, the polling.da. And just extend the send to send that information about sending, and add a receive definition for all messages received to send information about that receiving, okay, that's intercepting messages. And then checker can just specify the safety property as we discussed and check it anytime it wants. To check it at the end, you need to specify a condition to detect the end. So here is the first part about intercepting messages. And by the way, this is a complete this algo program. You can say import polling. Okay, the original program doesn't have to change. And for process P, we define process P to extend polling.p. Okay, so those has whatever the polling.p does. And we redefine a second method to take actual parameter checker, okay, and call the original setup for the responders. Okay, so this extended P process knows who the checker is. So now the send method is overridden to say send M to, this is a set of 2 processes to send. So just call super.send, that's the original send. And then this send information, send M to this guy with a logic time to checker. Okay, that's about the sending. And for receiving, you just say receive a message M, that match any message from some process. And you just add this extra send received M from a logic time to the checker. This way, all messages sent and received with these 4 components, the tag, the original message, the destination, or sender here, and the logic clock to the checker. Okay, that's all needed for the polar. And for poly, it's actually similar here. Okay, you can see this exactly the same. This also need to pass in checker. Remember, it didn't have a setup because it didn't have parameters, and but you still have to call it just to set up. And then the send is extended and receive handler is added. And here I made a little variation. Actually, the logic times are not needed, so I just didn't send that component. All right, that's the first half. And now the checker process. So the checker process needs to know the polar and the polys. That's all. Okay, and the termination condition. Since for this program, the poly is waiting to receive, or all the polys are waiting to receive the outcome. So I made this a wait for each responder, the polys. They have received, okay, from those guys, we have received them, that they received the outcome, okay. And then that's the end of the program when that's true, and you check S1 and S2. So here's definition S1 and S2. And if you look at this body, this is exactly like copied from the conditions we had written precisely before. And the only difference, remember the correspondence we had written in here? Okay, we changed this form to that form, and similarly. Okay, so these two are exactly like that, right? You send some question, okay, and P send some question, and P send some outcome, and you want to check each responder received from each responder received the reply. Okay, with the outcomes time is bigger than the reply time, and the same for S2, exactly like before. And now the main process, main method, I'm sorry, like before, except you create an actual checker process. And when you create responders and polars, you pass in the actual checker. And then you set up the checker by passing in the polars and polys and start a checker. Okay. And checking safety can have other variations and optimizations. So when you have a system with many processes, sending everything to one checker, that's the biggest bottleneck. You can use the hierarchy of checkers. So each checker observes a subset of original processes and or child checkers and reports to a parent checker. Okay, if you think about this, instead of just observe all the original processes and report the result, you just observe from other people and you just report to the parents. If you think about it, if you're computing some sum and you're accumulating the sum, this is exactly like map reduce. And it's very easy to implement in this algo. And optimization. So the most obvious ones, you want to omit parts of information that's not needed for checking. So for our example, the responder, actually, we already omitted logical times. You can omit more. You can actually omit all about sending that wasn't used. And you can omit all but the message content about the receiving. Okay, and for polar, you can omit the target process about sending and the actual question. It's never used, we just have a random reply. Okay, and so we discussed how to let the checker process extends the original processes. Okay, and here we can also let the original process extends a checker class. Okay, and this way you define the checker class and different original processes, right? Different implementation of same algorithm could extend it. And there you have to do small change to the original program. In each of the original process, you need to add the checker as a base class. And in the setup, add extra parameter to pass in the checker. And in the main, you create and set up the checker and pass in the checker as additional argument to the setup. Okay. And in general, of course, we could have a higher level language, write the ideal property specification and compile those to the executable code and doing the checking. Okay. Checking liveness. Remember, checking liveness boils down to checking safety plus timeouts. Okay, so here we discuss checking timeouts. And we talk about Now, first talk about, we do this based on the elapsed real time at the checker. Okay, using the same frameworks before, we extend the original processes to be checked, just like for checking safety. Okay, and plus additional specifications, the checks for timeouts. Okay, and in general, we can check two kinds of timeout. One is the timeout between observations of any two sending and receiving events. So when the checker receives event 1, it starts a timer in the separate threads. And when the timer times out, the thread would send a timeout message to the checker. When checker receives the timeout, it checks whether event 2 has been observed and reports a violation if not. Okay, this can generalize to check conditions involving multiple events, not just whether event 2 has been observed. You can check any condition. And then the second kind is, of course, the timeout of the entire execution. And all you have to do is you add a timeout to the weight of the condition for detecting the end. Okay, and this is the entire program to check the liveness properties. Okay, it looks big, but actually really simple. So first you import a threading, remember that needs for timer, and import a time module, again, for timing. And then there's a dictionary that maps each kind of timeouts to a particular time. This one is a 0.1 millisecond, okay? And this is from question to the first reply. And this is from question to the outcome, okay? This is 0.1 millisecond. This is actually 0.01 millisecond, okay? And the total is 1 second, just we set up this time. And then this checker process actually does the setup just like before for checking safety. And this method actually is exactly the same as for checking safety, except this time out, okay? And this condition was like before, you wait for this to end. Now we say, suppose you wait to end, you do nothing. But if it times out, look up the dictionary timeout for total, times out for that time, then output, hey, timed out for the entire execution, okay? So this is the same as before, except this timeout for total time. Now checking timeout between any two pairs of events. So remember the two on the check is from sending the question to receiving the first reply and receiving the outcome. So when you receive the first of the pair of event, which is sent a question, okay, and you can start two timers, okay, you run timer, these two timer with the name and any additional parameter you want to use for something or print out actually at the end, okay, and run timer just takes all arguments, okay, and starting a threads. In the threads, it is the real timer with passing the same argument and start running that thread. So here's a real timer, okay, we're passing the arguments, but these arguments are getting from here, that's the name and the rest of arguments. All it does is saying, sleep certain amount of time, which is using that name to look up the timeout in the timeout table, sleep that amount of time, and when that's finished, sign the timeout with that name and the rest of argument to self. Remember, this is in the checker itself, okay? So that's mostly done. So when the checker receives the timeout, okay, receive the first kind with some parameters, and just check that property it wants to check, okay? If it's supposed to have received some reply, okay? If it hasn't, not. Just say if not that condition, then report the first timeout. And the same for here, okay? It's supposed to have received outcome from each responder. And if not, you report a violation, okay? In fact, I did a tiny little shortcut just so it fits on one slide. All right, and there's also some variations and optimizations for checking liveness, okay? For sure, all those things you can do for checking safety applies here too, but you can have a little more. Optimization, and you can limit the common checks. For example, we can change the wait in run method. Okay, remember waiting that termination condition, and then with the timeout. So you can just change the whole thing to waiting for a timeout because that condition already checked by the other timeout for pairs of event. Okay, and in fact, you can see these two lines are the same. Right, this is the event you're waiting for, and this is the condition you're check. So these two lines are the same. You don't have to check two places. And in practice, we can also use real time at the original processes. This improves precision for events at the same process. Okay, to improve the overall clock precision, a clock synchronization algorithm can be used. Okay, one interesting thing to note about efficiency now, the same framework, okay, can be used to measure performance, do performance benchmarking. You simply observe the start and end of the entire execution, then you get a total execution time. You can actually measure and sum up the time durations between any pairs of events. Okay, so this whole thing about checking liveness really boils down to checking timeouts. In fact, timeouts is so essential to practice. Sometimes your system hangs, that's because it's waiting for a timeout. If it didn't have one, then you have to have a power button. Okay, and this is important even for centralized sequential program when it runs too long or gets into infinite loop. Okay, that's part 3. Now the last part, part 4. We'll discuss experiments and give a demo. Okay. So implementation. This algo is implemented as extension of Python. It has been used extensively in studying and teaching distributed algorithms, including this checking framework I talked about. Used extensively too, sometimes ad hocly and sometimes systematically. This algo is open source and easy to use. For example, you can simply add this algo root directly to the Python path after downloading from GitHub. Then you just run Python module DA polling.da. Okay, that's the polling program. For runtime checking, you run the checking program the same way. Okay, so in general, you really need 3 things to do the checking, right? You need the original algorithm plus some input, and that's the original executable program. And then you have the safety and liveness requirements written as functions and receives in those program I've shown. And additionally, you need a fault simulation. Okay, in this algo, this is executable configuration. On next slides. So fault simulation is really essential for checking in simulation of real distributed systems because failures do occur and you want to see if your program is working under all those situations. So process failures and link failures, okay? Process failure happens much less often than communication failures, link failures. Okay, they can be simulated with communication failures, okay? Because processes interact only through communications. For example, a crashed process can simply stop sending messages. It's the same as crashed. Okay, communication failures, you can use send to simulate all of those. Message loss, you just drop messages without sending. Message delay, you wait for some time before sending. Duplication, you send some messages multiple times. Reordering, delay some messages until some later messages are sent. Corruption, then you just change message before sending. You can even impersonate. You can set in a built-in sender when sending to simulate the Sybil attack. I put it green because it was an official feature in the language documentation. So an example, suppose process P drops 1% of messages it sent. Okay, you simply, remember we override the send, okay, and calling the super.send. So you can simply add a condition saying, oh, throw a dice randomly, and if it's less than 0.99, okay, I do the send. And the other 1% of the time, I don't do the send. I drop some messages. Okay, so this is the example for running safety and liveness check, both of them. Okay, and example output. So you run Python -m DA, the DA module, and this is my file name, polling check live. Check means checking safety, and live checking liveness.da. Okay, and so this shows I'm running this main process and it's initialized at this IP address, okay, and this transport number. and then start this module polling check live from this file, okay? And running iteration 1. This is pre-built in. You can set to run the same thing multiple times for performance reasons. This is a command line option. By default, it's just 1. And so now it's waiting for the remaining process to terminate. And you can anytime press Control break to force termination, kill the process. Okay. And so the shows now main process started. And remember, all we print out was when the sender received replies from all responders, it print who sent yes. So it received the yes from these 4 processes. Okay, and then send outcome to the responders. And each of responder just say what outcome they received. So each of those say that I received 4. See, these are all of them. And I also check liveness. In this particular case, actually the L2 times out, which means right L2 is waiting for after a question, waiting for all responders to receive the outcome. And in this case, it says I'm waiting for, remember the PS, which is a set of all processes, and witness process. Let me show you just a sec. Okay, L2 here. Okay, so it shows that at the bottom here, okay, it's PS and R. Okay, and so R is, right, not each R in RS has received the outcome. So you print R, which is a witness. There's one guy who didn't receive, one of the guys who didn't receive, okay? So this is the outcome here. In this particular example, it says A999008 didn't receive. So in this particular case, 1998 here, okay? So it didn't receive an outcome in time, okay? And then when await condition waits reply from all, and then it checks both S1, S2, and that's true. Okay, so here's a summary, okay? Checking both safety and liveness. And all I did was actually, I like the checker process for the liveness we've seen on the second piece of code about checking liveness. And that checker process simply extend the checker process for safety in the previous one. Okay, so it does all the interceptions already in the previous code. That doesn't have to do it. And all I did is to change the last line, which for the safety program, it checks at the end, prints S1, S2. For the liveness check, we didn't print them. So I just used the previous ones, they print out S1, S2. And here I have to use a super because those S1, S2 are defined in the checker process for safety check. Okay. And the result of running for this example output, as I already explained, safety checks S1, S2 at the end reports true, true. Liveness check L1 passes, so quietly, nothing happened. But L2 timed out, and the process, the last one was shown was the one of the witness that didn't receive outcome in time. Okay, and there are more other runs. If you increase the timer for receiving outcome from 0.1 millisecond to 0.01 second, then no outcome, no timeout was reported to in dozens of runs tried. And if you add a message loss rate of 10%, then you can see some total timeouts, or even sometimes all 3 timeouts happens because some message was lost. You never received all replies, okay? And so you can see this algo run, and you can run it yourself. And get to run this algo extremely easy. Thank you to fabulous Boolean and Python. And now it runs on Python 3.6 and 3.7. I'll give a demo that runs polling and checking safety and liveness. Okay, and anything exciting you have, if there's time afterwards, you can run. Actually, much more has been done unofficially by students in class, failure injection and other after class. Some students did more, actually, they like it. Backup restore, testing, debugging, visualization. I will show visualization, okay? And we have experimented with many well-known algorithms. In fact, just about all we or hundreds of students found interesting. We were really helped greatly in teaching and research by this algo. This included over 100 different course projects at Stony Brook, including some work by undergrad students or even high school students. Some of them didn't know programming at all. And this has been used externally too for both research and teaching, okay? In general, very few bugs have been found and fixed. So get and run this algo, just go to GitHub, look at the README, and you can just download, unzip, and run a script without even installation. Or to install it, you can just add to Python path, that's all. Or if you want to, you can run setup. Or you can even not install, you just use pip install for Python 3.7, you pre-install, but it's stable. We use this for many examples, okay? In general, you can go to the website and get the slides for tutorials and the whole language description in just a few pages. And if you like formal specification, there it is. Okay, I'll give a demo. But just before that, I'll give you some idea of some more algorithm in this algo, just quickly. For example, want to show you paxels are essentially just two pollings. Okay, this is the whole basic paxels are agreeing on one value. And you can see the proposer, which just send a prepare and wait for response. And this time wait for majority, okay? Count respond greater than half. And then calculate something so that it can send again. And the only thing important is the second time receive, it's not in the proposer, it's something else, but it's the same count and receive. Okay, send, wait for response, send, wait for response. And the acceptor, that's like responder, you receive prepare, you send back respond. Receive accept, you send back accepted. Okay, that's two pollings really. Okay, and create these processes. Let me just show you a little more interesting. This is the one you've just seen on basic paxels. I did a little grouping, okay? It's the same, just increasing spacing, put the queries together, and only color the queries instead of these keywords. So you can see this is send and wait for majority. And then before send again, you select something to send, or use queries, okay? And then here you wait for majority, actually it's the same code here. And same thing, when you come to the acceptor, when you receive prepare, you just send respond, except using query with some conditions to decide when to respond and what to respond. Okay, the same thing for the second one. All right, actually the same thing for multi-paxels. The replica is about your replica of the bank, for example, but here's multi-paxels. It's really just send and wait. And since multi, you have to do while true, keep doing it. You want your service to be live forever, so send and wait. And then here, since you're multiple, you send a bunch of things, and then you'll wait. And there are now more cases to wait. Okay, there's while true again, you have to keep waiting. And acceptors, you receive the first one, send back, receive, and send back. And there's something for computing max. By the way, this ballot, famous ballot, it's like logical clock. All right, some other examples, like Lamport's mutex is very famous. You can write in C code, the best C code versus this algo code. Actually, now it can do in 20 lines. And a lot of examples, this is from 2002, so paper or examples and previous well-known systems, especially Pascal and IO automata. And compiler times, then code, generate the code size, and performance of some examples, and some more student projects. The point was you can write 300 lines instead of 3,000 lines. And we even have a lot of things just for consensus because it's so important in practice, okay? And also security protocols too. And this was from last year. And since then, this has been used externally for teaching too, and even teaching discrete math this year. Okay, so part 5 now, try yourself. But I'll give you a demo, all right? So let's look at the program here. So let's first look at the polling example, polling.ba. Okay, you can see this is exactly the one you've seen in slides and by the way in the paper. Okay, this is the poller, this is the poly, and this is the main process. And so we can run this guy by, okay, let's just run this polling.ba. Okay, you see the output I explained each of those and run finished. And what's interesting was we have a visualization. So I can show you, I put in a separate file, just show you, see this.ba. So you can see this program is exactly the same as the other one. The only difference is here. I added this config visualize to be true. And this you have random colors. And I didn't use that. I configured it to say, hey, P process is orange and R process is light blue. So now if I run this guy, okay, suppose I want to run this one with this version. Okay. And so if I run it, it will do the same thing. And afterwards, it will automatically pop up a browser. See, this is the orange with the polar and this blue for the police, 10 of them. I guess my code says starting 10 of them. And then you can actually just use your right arrow to show the runs. Okay. So Polar sends questions to all police. Actually, I can make it bigger to start with. You can actually mouse over and see what's the message. Okay, question. Did you attend RV? Yes or no? Okay, and then continue with this poly replies. You can see the different replies. Oh, too big. Okay, and so when Polar receives replies from all, it's an outcome. Okay, and you can actually play backwards. All right, now let's see the checker. Oh, let's see the program with checking on. Okay, so polling check.va. So this program, it just has exactly extending P to add extra sent, okay, received, and then the checker, just wait for this condition to check S1, S2 at the end, and S1, S2 just as defined. You can see actually, here's more obviously just the ideal notation and this notation. And then this, the extended the checker that does this, okay. And there's also exactly a visualized version, check this.va. Again, it's exactly the same, except I have this visualize here. Okay, I guess I want to send to be black and RCVD to be blue. Okay, so let's run check version. I actually run before. Check, okay, check.da. And if you just run directly, this time it will just check at the end, say true, true. But if I wanted the check version also has a check with this, okay, and I run that, and it will run check and pop up browser with visualization information. See, it's the same as before, okay. But what's more interesting now, you'll notice, okay, a black one, okay, after the Polar sent questions to all police, and it also reports to checker I sent this. And these police replied, and it gets reports to the checker I sent this. Okay, and the blue ones is now the Polar received backs is also got to tell checker, hey, I received this. Okay, so this is it. I can see all that. Okay, and finally, the same green showed up, and again, each of these things you'll be told to the checker, okay, for checking. And finally, let's see the checking for safety and liveness. So this one, polling check live.va. See, all I did was we extend the checker to take this checker from polling check. So that's a safety checker. So this guy just have the liveness part, the timeout, didn't have to have anything else. Okay, and then this only thing changes S1, S2 now says super. Okay, and the same thing. I also have visualized version 2 is exactly the same with the same, except with the visualize at the end. Okay, so let's just run them again. Check live. Okay, so this checks both safety and liveness. So actually there's an L2 timeout here too. But let's run it with visualization. Okay, check live viz. So this will check safety and liveness and have visualization. Again, this one has a timeout. Okay, see. Okay, see now this is the same thing. Okay, And the only thing, remember this one has 2 little timeout messages. I don't know if you can see this, but we can make it really big for you to see that timeout message. Okay. Okay, here it is. Notice on the left. Okay. See, this one here is the first timeout message. Okay. QO timeout message. And then actually this time, this timeout message, this one, see here, because it's sent to itself. Okay. And this is the QR times out. Okay. All right, that's the demo. Okay. And you can just run all of these things yourself. Oh, indeed, see, this message took so long to get there. Okay. All right. Let me just finish this last. Okay, so you can get to run this yourself. And to conclude, this is a slide about ongoing and future work. Okay, we're still working on a lot of high-level features for simulation, testing, and visualization, and many additional and improved analysis and optimizations, in particular incrementalization. All that queries and checkings are expensive you do from scratch. This algo does some incrementalization, and it actually did more, if not because all these Python updates that's hard to maintain. Okay, and of course our interest is applications for real distributed algorithms, better understanding and specification of more algorithms, and also exact liveness properties and complexity guarantees. And in the long term, we hope to study systematic design optimization of distributed algorithms. So if you're interested in the compilers, equalization, we don't have time to talk about it all. And these are some papers. And mutual exclusion, logical clock, and Paxos, so these are well-known algorithms. But when we write in this algo, we actually find improvements, okay, both safety and liveness to previous descriptions, specifications, okay? And formal verification and checking. And this is our V paper, and this is our website. Thank you.